This is a lecture from OpenTuition. To benefit from the lecture, you should download the free lecture notes from opentuition.com.
This chapter deals with the topics of big data, linear regression, correlation, and time series analyses. First of all, big data. Now, the concept of big data is relatively recent, certainly within the last 10 years or so, and it was really initially kicked off by large supermarkets. Companies like Walmart in the United States began collecting a lot of information about their customers, and they did this by issuing their customers with loyalty cards, so that every time the customer checked out from the supermarket, purchases were rung up, they put through the loyalty card to get some points. But the real benefit to Walmart was not the loyalty that would make you keep coming back here. It was that they could record against each customer with their loyalty card exactly what they had bought. And this information, it's essentially historical information, which they would keep for at least 5 years. And then they could look at this information and deduce what particular customers were interested in. They could deduce perhaps whether or not you had a baby at home, depending on your purchases, or a pet, and so on, or whether you had a car. If you were purchasing, a car polish or something of that sort, then there's a reasonable chance that if you're doing that regularly, you actually have a car. So this is looking at extremely large collection of data that then can be analyzed by the computer to reveal patterns and trends and associations, especially relating to human behavior and interactions, and maybe in particular purchasing habits. There are two processes. First of all, you have to collect the data, like loyalty cards, or looking at the texts you send and looking at the words which you use in there will be another way of collecting a lot of data, or looking at the email, or your internet service provider knows every site you have visited, and so this data can be collected really very easily now through computer technology. And then with this huge amount of data, you have to try to make sense of it. It can be a bit like looking for a needle in a haystack. There may be something useful in there, but there's an awful lot of it is really pretty dull. And this analysis of the data to try and find something useful is called data mining. The storage of the data is in what's called a data warehouse. So data warehouse holding this vast amount of information, and then the data mining is a bit like gold mining. There's an awful lot of mud and rubbish to get through, but occasionally you'll find this precious nugget of gold in the middle of all this material that isn't really very valuable. The characteristics of big data are known by either the 3 V's or maybe the 4 V's. The 3 V's was the original model, which was set up by a researcher called Laney. And the characteristics were as follows. First of all, a huge variety of data. So it's not just what you've bought, but it's maybe in the supermarket, but it's maybe the time of day or the days of the week where you prefer to go. It will be saying how you normally pay. Is it cash or credit card or debit card, and so on. It may be able to track you as you go around the supermarket, because if you have a mobile phone and it's on, even if you're not using it, then it can determine where you are in the supermarket, which aisle you are, and it could tell the supermarket whether you have paused and looked at particular products, even if you haven't bought them. It will soon be the case that they will use facial recognition technology so that even as you come into the supermarket, it will recognize who you are, assuming you've been there before, obviously, and will be able to track you going around the supermarket, and will be able to see again which particular items you've perhaps expressed an interest in. Maybe you put it back on the shelf this time, but maybe if they email you a little 10% discount voucher, then maybe they will tip you over into buying it. So huge amounts of information. Again, you see it in mobile phone companies. They know who you've phoned. They know how long you've spent talking to them. It would be possible, if it were legal, for them to listen to what you're saying by computer and interpret some of the conversation. They know where in the country you are. And indeed, that sort of information has been used quite often by police forces to try to determine who might have been near a murder victim or something of that type. Obviously, this great variety of data means there's a huge volume of data which has to be held. Sophisticated IT techniques are needed to hold this amazing volume of data. It's held in what's called server farms. And many of the large IT companies are now beginning to locate these computer installations in northern hemispheres, in places up near the Arctic Circle, in Alaska, in the north of Canada, in the north of Norway, because up there the weather is colder, and this means that they can cool the machinery much more efficiently than having it, say, located in New York or Washington or Madrid or somewhere which is much warmer. And then we have the velocity. This data is being continually updated. Huge amounts of data coming in on a absolute continuous basis there. And it has to be processed, has to be capable to be processed reasonably quickly, because some buying habits or some particular interests might only last a few days. And you want to make use of that data, record it quickly, analyze it quickly, so that you can use the data quickly to try to increase your sales. Finally, some people add a fourth V, they call it veracity. We have to be confident that the data is truthful. Veracity means truthfulness, really. Are our data collection methods sufficiently robust that the data being recorded is relatively accurate? Because if it's not accurate, then of course any conclusions we're going to be drawing are pretty useless. The big data analytics, essentially this is the data mining really. How do we analyze this 5 years worth of historical data, recording everything that somebody has bought over the last 5 years? And this is in general known as I say, either data mining or big data analytics. And includes analyzing data to establish patterns and relationships. So, for example, it might be that when somebody comes in and they buy, let's say, lettuce and tomatoes, they also buy mayonnaise. Now, that is not something which is surprising, obviously, but supermarkets have occasionally been surprised at the relationships between different items being purchased. And then they have found, they've experimented and say, well, if I put these two items next to each other on the shelf, will that increase my sales? They can also be looking at how maybe sales vary over the week, over the year. They can be looking at how sales maybe vary according to the temperature. So if it's warm weather, people might be thinking, well, I'm going to have a barbecue, so they'll be buying that sort of food. If it's cold weather, they will tend to be buying food maybe which is more related to casseroles and stews and the like. And if you can try to predict, and this is where we're kind of getting on to this next one here, based on this analysis, maybe we can predict demand. So we hear from the weather forecast service that tomorrow or the weekend is going to be sunny. Then we know that lots of people are going to be coming in hoping to buy food suitable for picnics or barbecues. If we feel or hear from the weather forecast that the weekend is going to be snow and cold and so on, then the purchasing habits could be predicted to be very different, and we can make sure we have the right stock in to match the demand. There's text analytics, scanning texts and emails and word processing documents, even attachments, to see if we can extract useful information. Voice analytics is increasingly reliable. And then there are statistical analysis to try to identify trends and correlation changes in behavior. To show how powerful this can be, Google, for example, Google knows the kind of search terms that people are looking at. Google has often been able to identify when, say, an influenza epidemic is hitting a particular area before the health authorities do. Because if you're feeling under the weather, if you're feeling as though you're coming down with flu, then you maybe some people will go onto Google, they'll be looking for what sort of medicines or pain relief or whatever is good for influenza, or what might the symptoms be of a particular disease and so on. And because more people in a particular area of the country are searching for measles or flu or colds or whatever it's going to be, they can say, well, the people in that area of the country mustn't be feeling too well, and they can very quickly pick up the beginning of epidemics of diseases. Leaving big data aside, we now get on to look at something called linear regression. And linear regression tries to find a relationship between two variables. So here we have two variables, y and x, and the x here is supposed to be what's called the independent variable. And the y is supposed to be called the dependent. So an example would be, x could be the volume of goods you produce. So you decide on the volume of goods you produce, and the y could be the cost of production. So the cost depends on the volume which you are producing. In an earlier lecture, we looked at the temperature of the day or the week against the amount of electricity which was consumed. Well, there the temperature is the independent variable that causes changes in the amount of electricity which is going to be consumed to keep people warm. We've got two what's called coefficients, and there's two things to find to be able to define the linear regression here. We have got a and b. So if we were thinking that this independent variable was the volume produced, and the y here, the dependent one, was the cost of production here, then you can see that if x were naught, this here term would disappear, and you're just left with y equals a. So in this particular case, a would be the fixed cost, the cost which is going to be there for, let's say, the factory rent, even if you produce nothing. Every extra item you produce is going to increase the cost by b. So if you're producing 10 items, you'll be adding 10b to the total cost. And in terms of costing, b would be what's known as a variable cost, basically the extra cost that each extra unit is going to be causing. Now, the unfortunate thing about linear regression is it will draw the best straight line it can through any given set of points. So if I were to feed into the formula to do a linear regression on this, and if I were to put in your day of birth, 1 to say 365, leaving leap years out of it here, and if I was to put in your mobile number, here's two sets of variables: date of birth 1 to 365, depending when during the year you were born, and your mobile telephone number, essentially a pretty random number there. It's quite obvious that there should be no connection between these whatsoever. They're not related in any way. But linear regression will give you the best straight line it can that would join these up if these were on some sort of scatter graph. So if we were doing this on a scatter graph, your date of birth and your mobile phone number, presumably what you'd be getting is a kind of scatter graph where this would be kind of dotted all over the place. So here's your up to 365 in here. Here's your mobile telephone number here, and you'd expect something like, kind of this. It would be scattered essentially randomly on the scatter graph. But linear regression would say, well, what's the best line I can do? Maybe come out with that. And it's obviously kind of ridiculous to say that there's any relationship between those. What we need to do is to test how good the relationship is. And this is done by what's called a coefficient of correlation. So you really should not use any sort of linear regression formula or rely on a process of linear regression without doing coefficient of correlation. R can be between -1 through 0 up to +1. Okay, that's its range. If R is +1, you have got a perfect positive correlation. This would mean that if you were to put these out on a scatter graph, all of your readings would perfectly line up in a straight line. Not one of them would be off that straight line. If we have R -1, this means perfect negative correlation. This means as one variable increases, the other one decreases, but again everything would be precisely on a straight line. Perfect correlation. If R is 0, you're essentially dealing with the random points. There is no discernible pattern of association whatsoever between those variables. So that's R, the coefficient of correlation. Then there's R squared. So if we had, let's say, R equals 0.9, then obviously R squared is going to be 0.81. This means that 81% of the variation in one variable can be explained by the other. So one of the variables is going up and down, and 81% of that variation can be successfully explained by variation in the other. That means there's a 19% variation, which is presumably due to other effects, maybe random effects or errors in the readings and so on. So if R squared is low, if this was down in say 0.2, then one variable is not well associated with the other, and you can't put very much confidence into the linear regression line. If R is very high, up around the 0.8, 0.9, 0.95 and so on, then there's a much better fit, as it's called, relationship between the two variables. The more points you have, the better when you're doing linear regression. To put it kind of crudely, if you think we'd only 2 readings, then basically any fool can put a straight line between 2 points on a graph. And really, there's hardly any evidence there that the variables are going to be in any way related whatsoever. If, however, you have, let's say, 20 readings, and from those 20 readings, when you graph them out, most of those points are pretty well on a straight line, then you've got 20 little bits of evidence that there does seem to be a reasonable straight line relationship between the two variables, assuming that R is high. Extrapolation means predicting outside the range in which you have investigated. So, for example, if we have a volume here, and we have the cost up here. So this is volume of production and cost. And let's say we have got, reasonably straight line kind of here. Let's say the highest output here is 1,000, and maybe the lowest output is 100, something of that sort. And you can see these pretty well line up here. The linear regression line is probably going to be kind of something like that. And then you're asked to say, well, what will the cost be if the volume is, say, 1,500, which is going to be about there? All you can really do with linear regression is to assume that the line we have is going to continue out like that, that the straight line will be continued. But actually you've got very little evidence it's going to do that. It could be that a very high output, when you have to begin paying people overtime and running machines really hard and inefficiently, that actually maybe the cost starts to rise very, very steeply. So we're just saying we need to be careful. We have no evidence of really what happens out here. Interpolation is slightly different. Interpolation is saying, well, what would the cost be at this point here? Now, we don't have any readings at that point. We've got a reading here and a reading here, and we're in between two. Interpolation means in between or inside the range. I think you can see that the predictions we would make when we're interpolating are almost certainly going to be much more valuable, if you like, much more reliable than extrapolation. I mean, we've got lots of evidence down here, lots of evidence up there. It's very unlikely that the costs are going to kind of behave like that. Other known influences should be removed. So if we were having here volume, maybe from the year 2010 up to the year maybe 2018 or something, it's not just volume which is affecting the cost. There could be inflation in there. And if we want to find how volume influences cost, you'd have to strip out any known effects of inflation, which would be muddying the water. And finally, and very important in linear regression, even good correlation does not prove cause and effect, does not prove that one variable causes another one. And the example which is quite frequently given here, let me try and get rid of up here, we'll draw another graph up here. The example which is very frequently given to show how dangerous it potentially can be to assume that one variable causes another one is looking at something like the consumption of ice creams and people who are suffering from bad sunburn. So let's say we have our ice cream consumption here, and we have people who have to go to the hospital or something because of lay out in the sun too long, and if you were to look at the statistics, you could easily postulate we're going to get something like that. Very high degree of correlation, but it doesn't mean that eating ice cream causes sunburn. All it means is that both happen together on sunny days. So it's the sun coming out, the warm temperature, which makes people go and buy ice cream, and it's the sun beating down, which is liable to be causing excessive sunburn, so people have to go to the hospital to get it seen to. And you need to be very, very wary about this. I mean, in a business context, what you might have here is advertising expenditure, and what you might have here is sales. And the advertising manager says, look, I've been increasing the advertising expenditure, and look, the sales are increasing as well. And the advertising manager says, therefore, advertising causes better sales. Maybe it is. But what it might simply be is that the economy is coming out of recession. And that the advertising person is spending more because they feel the economy is coming out of recession, but people feel richer and they would have bought more anyway. There's no guarantee that the extra sales have been caused by the advertising. Maybe no one's seen the advertising for all we know. Now, to perform linear regression, you have to make use of equations, and these will be provided for you. And here they are. Here is the line y equals a plus bx. And here is how you find b, and here is how you find a. And it looks difficult. People get worried about what these zigzags are, called sigmas in here. We just need to be a little bit careful in our interpretation of the symbols. For example, on the bottom line here, sigma x squared is not the same as sigma x all squared. So what I'll do is I'll just do a very quick little example here, and then we'll see a slightly bigger example on the next slide. So if we had our x and our y, and let's say this one's going to be 5 and this one's going to be 10, say, and then we increase this one maybe to 8, and we're going to increase this one here maybe to 15. And you say, well, we need in here, well, we need sigma x. Sigma x means the sum of x. So in here, 13, that is going to be sigma x. We need here a sigma y. That means the sum of the y's here, which are going to be 25. And then we have a sigma x squared. So if we go over here and we look at x squared, that's going to be 25. X squared is going to be 64. Sigma x squared means the sum of x squared. So we're going to have in here 989, that is sigma x squared. What about this here? Sigma x all squared. Well, this is sigma x. So sigma x all squared would be 13 squared would be 169. What else do we need in here? And we need sigma xy. So over here you'd have xy. This means the sum of x times y. So 5 times 10 is 50. 8 times 15, I think, is 120. So this here is going to be sigma, the sum of xy. Anything else? I think we've got it. When here we've got sigma x times sigma y. So in here we have sigma x equals 13. We have sigma y equals 25. So sigma x times sigma y, 13 times 25, is that 325. It's not really difficult, it's just a little bit tedious, and you do have to just think carefully, particularly maybe, the difference between sigma x squared and sigma x all squared, and the difference between sigma xy and sigma x times sigma y, to make sure you don't get them mixed up. So, the example we actually have in here, it's the same one as you have in the notes, and I'm not going to spend ages going through it, but you have to work out basically B first, because if you look at the A formula here, it of course has got a B within it, so it has to go from B to A, is the way you're going to be doing it here. So here we have two variables. We seem to have for these months, we have one for this, I assume is going to be the volume produced or something of that sort. Here we have Y, which is maybe the costs there. And we go through and we just make sure we've got the XY, the sigma X times sigma Y, etc., as within that. So over here with X squared, so 4 times 4 is 16, 6 times 6 is 36, and so on. This down here is going to be your sigma X squared. This here is the sum of your Y squared, sigma Y squared, and so on, rather like the previous one. So here we have the 140. N, by the way, is the number of readings we have. So we have 7 now. Okay, 7 months, and N is 7. So 7 times sigma xy, so there's your xy, there is sigma xy, 1870, minus sigma x, sigma y. So sigma x is 28, the sum of this column. Sigma y is 420, the sum of that column. So it's minus 28 times 420. On the bottom we have 7 times sigma x squared, so 7 times 140. And then we need in here, maybe we're going to have in here sigma x all squared. So sigma x is 28, so it's going to be 28 times 28 within that. And this works B out at about 6.7, 6.8. So every extra unit, let's say, being made is costing about 6.78 more, if it's costs and volumes, or every extra 100, I suppose, being made. Once you've got the B, you can put it in to find the A. So the formula for A is going to be sigma y over n. So there's your sigma y, 420, divided by 7. Then you want B times sigma x. So we're going to have B, which is 6.7857. Sigma x, the sum of your x's, 28, going to be there, over that, and we have got 32. So we have y equals 32,857, presumably in thousands there, and we have our x there in hundreds, I beg your pardon, 32.8, it's going to be in hundreds, and the final formula is going to be that. Once you've done that, you don't need to do very much more before you find the coefficient of correlation. And here's a formula for the coefficient of correlation, and nearly all of these we have already here. This should be saying not at 2, but at 2 up there. So we had the sigma xy, we had the sigma x, the sigma y, with the sigma x squared, etc. The one that's remaining is the sigma y squared, which we put in there anyway. So again, we put that in there carefully, remembering there's a difference in here between sigma y squared and sigma y all squared. So sigma y squared is going to be 26550 in here. And we have in here sigma y all squared. Well, there's your sigma y, 420. So it should be in here, it should be 420 all squared within that. And that will work out B. R, I beg your pardon. And you see R is very high. It should never be more than 1. It should never be less than minus 1. We're up there at R equals 9.8 or 0.98. So 0.98 times 0.98. We've got in here the coefficient of determination, R squared, is coming in at about 96%. So there's a very, very high correlation between these two variables. So just in the notes, make sure you can follow where the figures come from, and that you can just put them into the form. It just takes a little bit of care to make sure you get them right.